In this video, we're going to talk about the circuit element known as an inductor and some of the properties of it. Now, when you have an inductor, unfortunately, there is no nice relationship using algebra that relates the current and the voltage, like Ohm's law. V equals IR is a really simple formula. Unfortunately, for the inductor and the capacitor, you need calculus in order to relate the current and the voltage. In particular, for the inductor, we have that the voltage is equal to the inductance times the derivative of the current. So you're used to V equals like IR. Here is V equals the derivative I times L. Very similar, but that derivative does make things more complicated. If you wanted to then reverse that process and solve for I in terms of V, you have to then integrate, right? Reverse the derivative with an integral, and we get this expression here. So it's a lot more annoying to deal with this than before, but it's this, it's a new concept, but it's very similar to the capacitor video we had already. There are a couple of important points here. Just like for the capacitor, how the voltage could not change instantaneously, for an inductor, the current cannot change instantaneously. So whatever your current is before the switch happens will be the same as the current after the switch happens on a circuit. The other important point is that when you're doing steady state analysis, with a DC source at least, an inductor acts as a short circuit. So you can just replace it with a short, and that's the same as the inductor there. Now the annoying problems with inductors are going to be when they give you either the current or the voltage and they ask you to go ahead and find the other one. This is basically the exact same thing as we just did with the capacitor in the other video. And so on the first one, when you are given current and asked to find voltage, based on this first rule there, we need to take the derivative of the current. And for that, as we saw in the other video, again, it's the slope, which we already worked out to be 50, negative 50, and positive 50. And if we go ahead and multiply those by the L, because the voltage is L times the derivative, so my L is half a Henry here, we are going to get a voltage here of 25 volts up to 1, then down to negative 25 volts from 1 to 3, and then back up 25 volts from 3 to 4. And since at this point the voltage is going to start staying constant forever, it never goes again, so that means the derivative constant is 0. So that quickly gives us our values here for the derivative, which is the voltage across the inductor. Just like before now, if we want to find the current, we're going to have to integrate the voltage. So we can write our voltage here as a piecewise function, just as we did the capacitor. It's basically the exact same problem here. 50t if t is between 0 and 1, negative 50t plus 100 if t is between 1 and 3, and then 50t minus, minus 50, 100, 100, 200 if t is between 3 and 4. So that gives us the function as a piecewise defined function. We then integrate each part, trying to find the current. And we have to not just integrate, but also divide by L, which is 0.5. So if we integrate 50t, it'd be 25t squared. Divide that by a half, it goes back up to 50t squared plus some constant. And then we're going to have a negative 50t squared plus 200t plus a different constant. So again, we're integrating, dividing by 0.5. We integrate, divide by 0.5. And then we're going to have some other constant here, C4. And then we go through the same work as before. I of 0 they give us that as 2. So C1 is 2, I of 1. If you plug in 1 into the first formula, it'd be 52. If you plug in 1 in the second formula, it'd be 150 plus C2. So C2 is going to equal to negative 98. If I plug in 3 here, I would have, let's see, 400, I'll just work it out. So plugging in 3 there, that's 9 times 50, 450 minus 1200, right? Plug in 3 there. That's a negative 750 plus C3. And if I plug in 3 to the first formula, that's going to be, working out all the details, are going to be 52. So C3 then is 802. And if you want to see what happens when you get to 4, then I of 4. I'm not even bothering trying to draw it. You saw in the capacitor one, drawing it was kind of a mess anyways, but we can at least find the formula for the current here. So if I plug in 4 into that formula, doing a little bit of work here, we'd have negative 800 plus C3 is 802, so it's going to be 2 is equal to C4. So our final answer then, the one I'd be looking for, is 50t squared plus 2, negative 50t squared plus 200t minus 98, then 50t squared minus 400t plus 802, and finally 2 there on the appropriate intervals. And so this is how you're going to handle these inductor problems. It's, again, basically the exact same as the capacitor version. It just switches which one you take derivative of and which one you take integral of between voltage and current.